Hello, everybody.
Hello.
Hi. All right. So I posted the final assignment on the Canvas website if people have been able to access it. Okay. So there are four problems. Please let me know if if you have any questions about any of the problems. I can of course choose to not answer a question if it's like how do you do number four or something like that. But like if anything's unclear, I'm happy to help, of course. Um, some and I'm hoping there's like a sort of variety of difficulty level for the problems, and um, uh, uh, and yeah, just please get started whenever you have time, so that you can kind of assess how long it's going to take you. Don't leave it till the last day, even though I think presumably could be done um, uh, in 3 hours or so. Um, so uh, yeah, any questions so far about the final assignment? Anything like that? Any other questions too? Okay, great. Um, all right, so let's pick up where we left off last time. So last time we defined the short space S.
Can you share your screen?
Yes, sorry. Sorry about that. So S is the short space. Um, it's all F functions from RD to C, say complex value functions such that F is in C infinity. And X alpha D beta F is bounded for every alpha beta multi-indices. Okay, so that's a short space, and one which I think of is a slightly enlarging the space of compactly supported smooth functions to those which have rapid decay as x goes to infinity. So those have rapid decay, and all the derivatives have rapid decay as x goes to infinity. So think of like the Gaussian functions, like e to the minus norm x squared, things like this, or Schwartz functions. Okay, so we had this last time. I want to, so we're getting to we're going to do the proof of the inversion theorem today, but we have a couple other preliminaries. One, I just want to um, just review convolution for a second. A couple additional properties about convolution that I don't think we covered before. So if I have two functions, phi and f, phi convolve with f of x is defined to be the integral of phi of x minus y f of y dy, which is equal to the integral of, under appropriate conditions, equal to the integral of phi of y f of x minus y dy. So a couple of facts I don't think I've expressed before. So I just I'm going to try and clarify when convolution makes sense, or conditions which make sense, and a couple other facts about it. So one is that what's the support of the convolution of two functions? Well, it's one fact is that it's contained in the support of phi. if I just add the supports plus the support of f, where this is where, so think of two compactly supported functions, convolving them together. Then when you convolve, or you convolve it, say, can take a compactly supported function, convolve with another, like a little bump function, and what you do is just you still get a compactly supported function, but you just it's blurred out, so the support is enlarged a bit with f. So here E plus F, this is set summation. This is a set of X plus Y such that X is in E, X is in F. So I'm just going to state some of these facts and you can check them. So when does this make sense? When does phi, so we discussed this a bit last time, or a couple times ago. When does phi convolve with F make sense? So what are the conditions you need on phi and F to make sense of this? Well, one way of thinking about this, so if phi is in L1 of RD, F is in LP of RD for some P between 1 and infinity, then so let's call this convolution definition star appropriately. Then star is absolutely convergent. It's integrable. And moreover, phi convolve with f in LP. So this is, in fact, an LP function. It's bounded by the L1 norm of phi times the LP norm of f. So this is a version of what's called Young's inequality. So for p equals 1, let me say it like this. For p equals infinity, it's true. For p equals 1, so you could just, for p equals infinity, you could just put absolute values through the inside the integral and pull out the L infinity norm of f. So right, just take absolute values inside the integral here, pull out the L infinity norm of f, and then you're left with the L1 norm of phi. So it's not hard to see this for p equals infinity. For p equals 1, it follows from Fubini. Fubini's theorem. And then for p in between 1 and infinity, so it can be deduced from the two edge cases via the what's called the Restorin interpolation theorem. And this, I'm not going to prove the interpolation theorem today, but this there's a wide class of theorems called interpolation theorems. This is usually taught in a graduate, say, functional analysis class or something. Can look it up. These interpolation theorems often have somewhat involved proofs. Sorry, I may have made some typos earlier. Involved proofs that are often not too illuminating. Sorry, I see there's a typo up here. Thank you for pointing this out. Y and F, yeah. Thank you, Samuel and Michael, for catching that. Okay, so so under these conditions, convolution makes sense, and you can it tells you also what type of function the convolution is. You get an LP function if you start off with an LP function and an L1 function. So this is one notion that makes sense. Two, if you take phi, say, is compactly supported, and F is an L1 look, and then in this place is continuous, and you can prove this via the dominated convergence theorem. Okay, and let me actually prove a lemma. That if phi is in C infinity, F is in L1 loc, then in fact phi convolve with F is in C infinity, and d alpha is equal to convolve with F. So you can place, so when you convolve with a smoother function, the convolution of two functions together is as smooth as the smoother of the two functions. So you can, so in particular, this is often you say if you could convolve, take F, convolve with a nice smooth function that's akin to like an approximate identity, but smooth, then you know that the resulting thing, the object that you get is close to F, right? Because you achieve F in the limit as the approximate identity, as you tend to the, as you let say approximate identity parameters like delta greater than zero. If you let delta go to the zero, you recover F again. So a smooth approximate identity convolved with F you can think of that as smoothing out a function. Okay, so let's do the proof of this lemma. So the proof is, let's call d of h is 1 over h times phi convolved with F of x plus h. So I'm going to try and take the derivative of a convolution. Phi convolved with f of x. And what's this equal to? This is equal to 1 over h integral of phi of x plus h minus y minus phi of x plus h. Sorry, x minus y. Maybe I'll put the h inside. F of y dy. And this whole thing or maybe what I want to say is that this input here is less than or equal in absolute value. The absolute value of this is less than or equal to, say, the L infinity norm of phi prime by the mean value theorem. This. So for fixed h, no, sorry, for fixed x, and h, say, just smaller than 1, the support of let's call this AH is 1 over H phi of x plus y minus h, x plus h minus y, sorry, x plus h minus y minus phi of x minus y satisfies support of AH is inside of K equals, say, the ball around x of radius 1 plus the support of phi. Okay. Therefore, the integrand AH times F satisfies phi prime L infinity times chi k, the indicator function on the on this set K, times absolute F, and now apply the dominating convergence theorem. So limit as h goes to 0, dh is equal to f of y times phi prime x minus y dy. So I'm doing the proof when dimension equals 1, alpha equals 1. One second. Okay, notability is back. Okay, and so a corollary of this is that if I take f and g Schwartz functions, then f convolve with g is a Schwartz function. Proof. By the previous lemma, the derivative is okay. Are okay, and it suffices to show that 1 plus x to the n times is bounded for every n. And I'll leave this as an exercise. You take two Schwartz functions together, take two Schwartz functions, you convolve them, you get back a Schwartz function. Okay, so what's so I'm discussing convolution because I want to tell you how it plays together with the Fourier transform. So convolution and the Fourier transform. So if I take f, g, and L1, then f convolve with g hat is equal to f hat g hat. If I take f and g Schwartz functions, f times g hat is equal to, so I'll call this 1, is equal to f hat convolve with g hat. And I'll call this 2. So in particular, both identities hold when I in the case of Schwartz functions. So 1 follows from Fubini. So you see you have two integrals there, and you just interchange them. And using the fact that both you have two L1 functions to justify the application of Fubini. And 2 follows from 1 plus Fourier inversion. Which we are getting to. So I'll deduce 2 as a corollary of the inversion theorem, which we are going to prove almost now. So one more lemma. Well, there'll be a couple lemmas, but they'll be all part of the proof of the proving the inversion theorem. So lemma. So let me just emphasize that this is nice structure, right? Taking Fourier transform turns convolution into a product, and Fourier transform of a product is convolution of the Fourier transforms. So these two operations are product and convolution are dual to each other with respect to Fourier transform. The lemma, or so let's call this lemma 1 maybe. If I take phi in Short's class, integral of phi is equal to 1, then if f is in continuous functions of Rd, and f of x goes to 0 as x goes to infinity, then if we let phi delta of x to be the L1 rescaling of phi, so delta to the minus d x over delta, then phi delta convolve with f tends to f uniformly. This is what I was mentioning a second ago, as delta goes to 0. And the proof of this is same proof as for phi delta equal approximate identity. Well, or maybe I could just say this as phi delta, phi in this phi delta is an approximate identity. Such phi deltas are approximate identities. Take a Schwartz function with normalized mass, unit mass, then you could just obtain a Schwartz function by doing the proper rescaling. You obtain a approximate identity by just the rescalings. And note that these rescalings leave the L1 norm invariant. So this particular scaling means that the L1 norm doesn't change. Okay, so this is one way of obtaining approximate identity is just take a Schwartz function, have it with normalized, so it has as unit mass, and then rescale it. You do the L1 rescaling, and then you obtain approximate identity. And you can in particular apply all the things you know about approximate identities, namely if you convolve with a function, then you have uniform convergence. If you convolve with a continuous function, you have uniform convergence. If you convolve with an L1 function, then you have convergence on a dense set, or rather, you have convergence almost everywhere. Okay, so now let's state again the Fourier inversion theorem. For inversion, if f is an L1, its Fourier transform is an L1, then for almost every x in Rd, so this formula holds almost everywhere, f of x is equal to f hat of c e to the 2 pi I x dot c dx. So you can recover the function back from its Fourier transform. Equivalently, f hat hat of x is equal to f of minus x. This is another way of writing the inversion formula, given the way we defined the Fourier transform. Okay, so a few more a few more lemmas. Let me erase lemma. Maybe let me call this lemma 2. Lemma 2. The Gaussian function e to the minus pi norm x squared, or sorry, let me just make this function on R. X squared satisfies. I love the argument that gives this theorem: minus pi x squared minus infinity to infinity equals 1. So this function integrates to 1. So yeah, put the x here. Right, this is a non-trivial lemma, right? Because there's you probably learned in calculus class that there's no antiderivative for such a function. So you need to be clever to compute the integral somehow. And the proof is very clever, or a proof is very clever. So we prove it by squaring it. So let's take this integral, square it. So what's that equal to? This is equal, and then we do this, we do an amazing trick, is we just relabel the dummy variables times, so I just take this number, multiply it by itself, e to the minus pi y squared dy. I call one dummy variable x, one dummy variable y. And I write this now as e to the minus pi x squared plus y squared dy. And now I, sorry, dx, dx dy, sorry. There's a double integral dx dy. So I just wrote two copies of the integral, and now I'm expressing it as a double integral using Fubini's theorem. Now, I do change of variables. So I note that, well, this looks like this is an integral over R2. I could think of this as an integral over R2. And this just looks like the length squared of a vector in R2, of the vector xy in R2. So I'm going to write this. I remember from my calculus class that it's convenient to evaluate such integrals using polar coordinates. So polar coordinates on R2 R is x squared plus y squared. And so this is the angular variable. So x equals r cosine theta, y equals r sine theta. Then I remember how to do polar coordinates from calculus. This is the integral from 0 to 2 pi. Theta runs from 0 to 2 pi. Integral from 0 to infinity. E to the minus pi r squared. But I need to remember to change the measure as well. R dr d theta. Right, the volume form on R2 in polar coordinates is expressed as r dr d theta. And then this is equal to 1 over 2 pi integral from 0 to 2 pi, integral from 0 to infinity, And now I can see it. I can do fundamental theorem. This is d by dr of e to the minus pi r squared. Yeah, yeah. Dr d theta. Right, because I differentiate pi r squared, I get 2 pi r. Right, I get 2 pi r times this times the thing. Divided by 1 over 2. And then this is, I apply the fundamental theorem. I evaluate this object at 0, r equals 0, I get 1. I evaluate it at infinity, or I take a limit as r goes to infinity, I get 0. So I just get 1 from in here. And then this outer integral integrates to 1 as well, because I have integral of 1 of 2 pi, and I've divided by 1 over 2 pi. So this is just equal to 1. So it's kind of an amazing argument. It's like just the silliest possible trick, and it works. All right. Okay, and then the next lemma 3, is using this lemma. I can show that if I let f of x, let's call this g for Gaussian. Let g of x be equal to e to the minus pi x squared, then the Fourier transform g hat of xi is equal to e to the minus pi xi squared. That's cool. It's a function. This function, you take its Fourier transform, you get the function back again. So the Fourier transform of the Gaussian function is just another Gaussian function. So this is a beautiful example. My favorite proof of this, there's a bunch of different ways to prove this, of course. My favorite proofs are the one where I can do contour integration and complex analysis. So there's an easy proof using contour integration. So all the things you have trouble computing integrals of when you use contour integration, somehow this becomes easy proof using I'll give a different proof since might not all have seen taken 112, for example. Easy proof using contour integration. So this is complex analysis. And the fact above and lemma. So you need lemma 2. You need contour integration and lemma 2. Okay, a somewhat less elegant proof. Less elegant proof, maybe less elegant proof. So complex, I think like complex analysis arguments are somehow the highest art, but slightly less elegant form of art is an ODE argument. So another proof is we're gonna do use an ODE argument, set up an ODE argument. So so even if this proof is pretty elegant too, it's less elegant than complex analysis one in my for my taste. So let's let f of c equal shoot, I screwed up my notation. Let's let f of c be capital F of c be I'll call it g hat of c. So g of x is equal to e to the minus pi x squared. So I'll define this function capital F as g hat of c, just so I can not write hats everywhere for a moment, which is, remember, this is e to the minus pi x squared, e to the minus 2 pi I x c dx. Then note that f of 0, if I evaluate as like c equals 0, equals 1 by lemma 2. If I just plug in c equals 0, then I'm just integrating e to the minus pi x squared, and I get 1. So this function capital F is 0, at 0 is 1. And now I'm just going to take its derivative. And I'm going to see if I'm going to try and get an ODE for capital F. So G um, G prime of x is equal to minus 2 pi, take the derivative of the Gaussian function, minus 2 pi x times g of x. I just get the Gaussian 2 pi x times the Gaussian function back again. So because of this, so capital F prime c is equal to integral from minus infinity g of x minus 2 pi I of x e to the minus 2 pi I x times c dx. So if I take the c derivative, the derivative falls on this factor, but this factor comes down, which is nothing other than, and I see g prime appearing here. This is equal to I times, what do I have? I times integral from minus infinity to infinity of g prime of x e to the minus 2 pi I xc dx. Okay, and then therefore, okay, let me tell you why, let me refine my reason why this argument is a little bit less elegant than the contour integration one, is that this is a clever argument. Too. This argument has some cleverness in it. So, okay, so f prime of c is equal to this. So therefore, capital F prime of c is equal to I times 2 pi I c g hat of c, which is equal to, right, because I take the Fourier transform of the derivative is just 2 pi I times c times the Fourier transform of a function, which is equal to minus, now the i's cancel, so it's 2 pi c times f of c. So now I have my ODE. So therefore, I have, let me rewrite this all. I have f prime of c is equal to minus 2 pi c f of c, and f of 0 is equal to 1. Okay, so how do I solve this ODE? Well, I can find an integrating factor. So if I let g of c to be equal to f of c times e to the pi c squared, then g prime of c is just equal to 0. Let me call this star by star and product rule. Okay, so this is the method of integrating factors for solving an ODE. So this implies that g prime, so g is constant. So g has 0 derivative, so g is constant. But g of 0 is equal to 1, since f of 0 is equal to 1, which means that f of c is equal to e to the minus pi c squared. So g of so g of 0 is equal to 1. So this means that g of c is equal to 1. It's constant. It's equal to 1 and 0, so it's equal to 1 everywhere for every c. So that, and this completes the proof. So this is equal to, remember, just by definition, this is just g hack c. So that's the proof of the theorem. The Gaussian function is its own Fourier transform. Almost there. So lemma 4 is that if I take f in L1, it's a general lemma, g in L1, just f and g, anything, any L1 functions, then integral of f x g hat of x dx is equal to integral of so you can switch, you can move, right? If I have an integral of f times g hat, then it's the same as the integral of f hat times g hat, f hat times g. And the proof of this is again Fubini. Okay, now the proof of the inversion. So let's let I delta of x be equal to fxc times e to the 2 pi I x c. So the thing that we want to evaluate, but I'm going to include a Gaussian factor in here. So e to the, I'm going to squeeze in e to the minus pi. This is where delta comes in. Delta squared, absolute x squared, absolute c squared, sorry. Absolute c squared dc. And now we're going to evaluate the limit as delta goes to 0 in 2 ways. Okay, on the one hand, as delta goes to 0 by the dominated convergence theorem, and here we use the fact that since f hat is in L1, I delta of x tends to integral of f hat of c e to the 2 pi I x dot c dc as delta goes to 0. So just letting delta goes to 0, that's right, because the integrand, I have this pointwise convergence, right? The only delta dependence is here. And as I let delta go to 0 for each fixed c, as delta goes to 0, this thing tends to 1, right? Because I guess get e to the minus 0, which is just 1. So this is, so I use the dominant convergence theorem and the pointwise convergence of this thing to 1 to deduce that this is, I recover this integral. So the other, I want to evaluate this some other way and show that I recover f. I recover the function f of x as delta goes to 0, and then I'll be done because by the uniqueness of limits. So now fix an x, and delta, and let what do I want to fix epsilon? My notes are a little confusing. So let's the fix x and let g delta of c to be equal to e to the minus pi delta norm of c squared times e to the 2 pi I x dot c. So for each fixed x, consider this function. Then I delta of x is equal to, I claim this is equal to, sorry, yeah. So I delta x, is equal on the one hand f hat of xc times g delta of xc dxc. But on the other hand, I can move the hats, so this is equal to f of x. Let me call this y. Sorry, f of y times g delta hat of y dy, and this is by lemma 4.
You had I think a delta squared originally in your definition of I delta. Can you check that?
Yeah, let me. It's a typo here.
Okay.
Sorry. So this is, yeah, you're right. This delta squared.
Okay.
So I wanted to just get I delta right. Thanks, Michael. Yeah. So there should be e to the minus pi delta squared c squared, and then so what is so now I want to compute the Fourier transform of this. So um, what is g delta hat of y? So note that g of c is equal to it's this. Remember, we computed these identities if you last time. It's just multiplication by this phase of this function, right? So it's so e, it's this phase function ex of c um, times what I'll call k delta hat of c, where let's like k delta hat of c to be equal to e to the minus pi delta squared c squared. Um, so this means that g hat, this is g delta, g hat delta of y is just equal to k um, hat uh, sorry, so it's k, let me call this k, so I got my sign correct here. This is k twiddle hat of no, sorry, this is notation. So I'm defining this to be k hat. I'll call this k hat delta of y minus x, which is equal to, I'll just define this function. This is k delta of x minus y, where k delta of z is equal to 1 over delta times e to the minus pi z over delta squared. Okay, and let me yeah. So this is I'm just sorry. I'm just doing the proof for d. In the notes, my notes I just did the proof for d equals 1. That's the same proof. Okay. Okay. So now what? So therefore, what do I have? I have written I delta of x as equal to f convolved with k delta. So I rewrote this I delta as a convolution. So this is just a little trickery using the identities we proved about the Fourier transform. One, I move the hats over, and then I note that if I have a function like this, I take Fourier transform of it, it turns into this multiplication by phase on one side turns into translation in space on the other side. And forgive me here. This is just some notational ugliness. Um, maybe I should have been a little bit more careful about how to define things. Um, so then, okay, but this is nice, right? Because this is a nice this is a Schwartz function, right? The k, uh, this is just this is this is a Schwartz function, and in particular, it's an approximate identity. It's a good kernel, in fact. So therefore, um, I delta convolve with f now one. Oh shoot! So let me just change this. I'll just gonna correct it. So I'm doing it in dimension d. Uh, so I delta tends to f and L1 as delta tends to 0. Therefore, and we note that uh, tends to f almost everywhere, right? In particular, of almost everywhere convergence. So this completes the proof. In particular, if f is Schwartz, we have I delta for every x in RD. Right, or in fact, even if we just have if f is just a continuous function, if f were a continuous function, this would hold. But particularly for Schwartz functions, you have the inversion formula holds for every x. So it holds in L1. It holds almost everywhere. If you have any continuity of f, then it holds everywhere. Okay, so any questions about this proof? This was pretty tricky.
Could you just go back through the stuff you did after you like switched where the hat went?
Yeah. This last page, this kind of last page here, right?
Yeah. Um, so it seems like the goal would just be to compute G delta hat and then put that in. Is that what we did?
That's all we did. Yeah,
Okay.
that's all we did. We just computed G delta at. I introduced more letters, basically, but we just computed G delta hat, and the point is that you might remember this identity from a few days ago. If you multiply by one of these factors, multiply a function by one of these factors, and then take Fourier transform, it turns into translating by x after taking Fourier transform, and vice versa, right? If you take a function, have it consider the function where you translate it by y, and then take Fourier transform, you end up being multiplied by a factor like this, by a phase factor like this on the other side. So that's all we did. Is G delta was this Gaussian times this phase function. We take Fourier transform, it ends up being just this the Fourier transform of this object um, translated. And the Fourier transform of this object is um, so it's a Gaussian that's rescaled, right, by delta. And so if you rescale a function, take Fourier transform, what happens? You get you have to do the opposite scaling and then multiply by this dimensional correction thing, 1 over delta to the d.
Okay.
So we had to use a kind of a bunch of all of these, and then there was this reflection business that we used as well. So there's a lot of we use all these actions of symmetries and for mixture of applying symmetries and Fourier transform to compute the Fourier transform of G delta C.
Okay.
Right. So I did this, I think, pretty awkwardly since I introduced this K because I wanted to call to mind approximate identity or convolution with the kernel, etc. But that's all we did. was we computed g hat delta. We saw that it was equal to an approximate identity, um, and
Mhm.
then we concluded. Um, so the thing is that it's an approximate identity. Yeah. So this is the inversion theorem. Um, and it just you see it just uses a lot of uh, a lot of stuff to prove it's not it's not easy theorem. Um, okay, so corollaries. So corollary one, if f is in L1, if we let I delta x as in proof, then I delta um, of x tends to f in L1 without any assumption, without um, that f hat is in L1. So in the second part of the proof, we didn't use the fact that f hat was in L1, and this is called this just has a name. This is called the Gaussian um, summability. Summability of f hat to f. So if you have f in L1, you can define the Fourier transform f hat, right? And then I can take I just showed in the second part of the proof that I can recover f by introducing this function I delta of x and then taking which I wrote as a convolution of f with a kernel and then take a limit as delta goes to 0 and I can recover f again. So what should maybe maybe this is not so clear, but does this call to mind anything that we did with Fourier series? This is a hard question, or it's kind of an open, not a question.
Is it related to the Poisson kernel?
Exactly. Yeah. So a Bell sum ability, right? This is just like a Bell sum ability, where we didn't we the thing that's missing is we don't what we're not saying. Uh, so whereas the inversion theorem itself is akin to saying well, we have uniform convergence of Fourier series to back to the function. Um, recovering f as a limit as delta goes to 0 looks a lot like just we just modified the we just kind of modified the type of limit we took, right, in a way. We just modified the type of limit that we modify the sense in which we recover f back from its Fourier transform. We're still recovering f back from its Fourier transform, but we're recovering it by kind of looking seemingly artificially introducing this factor and then taking a limit, just like in a Bell summation, we kind of artificially introduce these factors r to the delta, or r to the k rather, and then take a limit. So what's missing then to what the place where we use the fact that f hat is in L1, which is like using the uniform or the little L1 summability of the Fourier coefficients is in step 1 here when we're saying well actually I delta um, tends to this object. So this is kind of like this part 1 is kind of like assuming that you have absolute summability of Fourier coefficients, and part 2 is kind of like the proof that the Abel sums of a continuous function converge back to or the bell sums of an interval function converge back to the function itself. Okay. All right, excellent. So this is analogous to a bell or Cesaro, I guess, where right in the lambda Fourier series, we just kind of manufactured a good kernel, and that's exactly what we did here. We manufactured a good kernel. Okay, so corollary 2. If a uniqueness theorem, if f is none and f hat of c is equal to 0, is just identically 0, then f is equal to 0. So, so in particular, the mapping is injective. Right, and corollary 3 is surjectivity of the Fourier transform on the Schwartz space. So if I define script f as a mapping from the Schwartz space to the Schwartz space, where script f of f is equal to f hat. So it's just a mapping where my inputs are functions and my outputs are functions. Is 1-to-1 and onto. So it's a bijection. So the corollary 2 tells me it's 1-to-1, and corollary 3 will show that it's onto, and this is a corollary 3 is a corollary of the inversion formula. So the proof is just if I take f in the Schwartz space, call capital F is f of minus x, then let G is capital F hat, then G is in the Schwartz space, we know, and G hat of x is equal to F hat of x, which is equal to F of minus x, which is equal to F of x. Okay. So in particular, what I've shown you, I can take any function of Schwartz space and write it as the Fourier transform of some other Schwartz function. So this is showing me, hence script f is onto mapping. So the Schwartz space is really a natural class of functions which I consider the Fourier transform. The Fourier transform is a bijection from the Schwartz space to itself. And finally, corollary 4 is that identity 2 that I wrote at the beginning. So if I take f and g are Schwartz functions, then f times g hat is equal to f hat convolve with g hat. And the proof of this is again via the inversion formula. So f hat convolve with g hat. If I take Fourier transform of this and evaluate it at minus x, then I get f hat minus x times g hat minus x, which is equal to, by the inversion theorem, f of x, g of x. So therefore, f like this is equal to FG hat. So again, this is all falling from the inversion theorem. And the last corollary, which maybe we shouldn't call this a corollary anymore, but a theorem, it's not a corollary, it's an important theorem, is not only is this map a bijection of the short space, but it's also an isometry. In particular, preserves the L2 norm. If I think of the um, so this is the Plancherel theorem, and the analog of this in Fourier series is Parseval's identity. Plancherel. If f and g so first we're going to discuss this for Schwartz functions, and then we're going to use this to extend the Fourier transform to L2 functions. So if f and g are Schwartz, then f hat times g hat bar the L2 inner product of f hat and g hat is equal to the inner product of fg bar. In particular, if f equals g, the L2 norm of f hat and RD is equal to the L2 norm of f. So the Fourier transform as a map preserves the L2 on the Schwartz class preserves the L2 norm. And the proof is again going to be pretty quick from the inversion, just our bag of tricks in the inversion formula. So by the inversion, f of x, g of x bar, so the inner product of f and g, L2 inner product of f and g, is equal to, I can, so I'm just using the inversion form to write f is f hat hat of minus x. Okay, and then this is equal to, I can just move the hat over. Or rather, let me change variables first. This is f hat hat of x, g of minus x bar dx. So f g bar is equal to f hat hat times g twiddle bar, sorry. What am I doing here? Let me just call this G. Let me I'm just going to change my notation. Let me remove the bar from there and put a bar here. Sorry if this is confusing. This is just a bunch of trickery. We've already done the key step. Now we're just going to move the hat over. So that's the key step. So this is equal to f hat g twiddle hat, and this is equal to f hat g hat. So I have to understand what taking complex conjugate does with the argument. So g hat bar, since g twiddle hat is equal to g hat bar. Okay, you can check these identities. And this is the so the Plancherel theorem you can think of as being the inversion theorem. Just put two hats on f and then move the hat over and then keep track of the minus sign somehow. And bars, minus sign and complex conjugate. That's all it is. Just move that. Put two hats on f, move one hat over. That's you can always remember how to prove Plancherel like that once you know the inversion theorem, inversion formula. Okay. So what have we any questions about this? This was this is really a corollary of the inversion formula. Um, so the comment, so the remark is that the Fourier transform restricted to Schwartz functions is an isometry in L2 norm. Since the Schwartz class, so remember compactly supported, C infinity compactly supported functions are dense in L2. So in particular, the Schwartz space is dense in L2. So since S is dense in L2, this suggests, so the next goal is we want to define the Fourier transform of an L2 function. This suggests a way to do this. This suggests a natural extension of the mapping F, which is the taking function associated with its Fourier transform to L2. All right, and note that we don't know how to take Fourier transform of an L2 function yet, right? Because we know how to take Fourier transform of an L1 function. We need that integral to converge, to be convergent, to make sense. We didn't know the integral, integrating a function times e to the minus 2 pi x times xc is a convergent integral. That's an integrable function. If f is an L1 function, then okay, that's integrable. But if it's an L2 function, we don't know, right? There's no obvious way to make sense of that integral. Okay, but what we're going to do is say, well, we can understand the Fourier we can take Fourier transform of the Schwartz function. So, and since this is a dense class in L2, and in fact this preserves norm, we'll try to we'll define the Fourier transform of an L2 function as some sort of limiting process of Schwartz functions by approximation. So, theorem, there exists and a unique, so this is important. So there exists a unique bounded linear operator script f from L2 to L2 such that, so this is an so we're going to view this as an extension of the Fourier mapping given by Fourier transform in the Schwartz space, such that when I restrict to the Schwartz class, f of f is equal to f hat when f is a Schwartz function. So this linear operator is just taking the Fourier transform when the input is a Schwartz function with the properties. So with the following properties. One, f is unitary. So, and two, well, I also know one other class of functions for which I can make sense of the Fourier transform. It's when f happens to be an L1 too, right? So I want want script f of f to be equal to f hat if f is not necessarily a nice smooth decaying Schwartz function, but is an L2 intersect L1. So if I know if f is an L2 function that happens to be an L1 function, I want this operator to also be just a Fourier transform. And the content of the theorem is that there's a unique way to define such a function script f. Okay. Okay. Oh dear. Okay, so the proof in my notes is like 5 pages long, which usually translates to like 8 pages of notes and notability. so perhaps we um, so perhaps we should do this, discuss this a little bit next time. Um, it's just a bit of Hilbert space theory. Um, yeah, I think I might assign. So maybe I'll state this theorem. Um, the key ingredients is like the density of the Short's class in L2. Um, yeah, so maybe let me just say, so the proof goes as follows. So maybe rather than going through the whole proof right now, let me just tell you kind of what you have to do. So it might seem not obvious to say, well, I can just find such an extension. Well, okay, there's only, and if you think about it a little bit, there's really only kind of one thing to try is take a limit. Okay, take a sequence of Schwartz functions, take an L2 function, take a sequence of Schwartz functions approximating that L2 function, and then just see what happens for this by applying the Fourier transform to that sequence, right? And what you want is for that to be convergent, right? You want that process to converge in L2, and then you define the limiting object as the Fourier transform of the function of the L2 function. So we'll show if Fn is a sequence in S such that Fn converges to F in L2, then is convergent in L2 to a function we'll define, we'll just call the limit f of f. And here f naught is just the Fourier transform. Restricted to S, restricted to Short's class. So this is the idea for the proof is just use density, take a convergent sequence, apply Fourier transform to that sequence, and try and show that this new sequence you get also is convergent. And you just define the and then everything is great if it's convergent because you have a convergent sequence have unique limits, right? And so you just define that limiting object as the Fourier transform of an L2 function. Okay, that being said, it's a bit of a work. It's a bit of work to do this. Somewhat, I guess. Somewhat some work. Yeah, it's just where a lot of the work is similar to stuff we've done. We're going to approximate f and L2 by some nicer functions. We're going to then smooth out that function to make a Schwartz function by convolving with an approximate identity, and then use properties of approximate identities to take limits in L2. So that's the gist. It's actually not so bad. And then it's and maybe I should just say that this is a manifestation of a more general principle that if you have Hilbert spaces, a linear transformation on Hilbert spaces if you have a linear transformation on a dense subset of a Hilbert space, then there's a unique extension to the whole Hilbert space of that linear transformation. So this is in fact like we can do this explicitly in L2, but it's also a consequence of some more general Hilbert space theory as well. Okay, so I'll stop there and we'll pick up again next class Tuesday, which is the last class of the semester. And you can turn your PSETs, your final assignments in anytime on Tuesday, and then I'll grade them sometime Wednesday or Thursday or Friday or something like that. And that'll be it. Okay, so I also have office hours at 4, or at 4:05 as usual, and there'll be at least one presentation of a homework problem in office hours. Any questions?
Professor, may I ask a question?
Yes.
Yeah. So you showed that there is a nice property related with Schwarz space. We can take Fourier transform and come back to the original function. But we also said that we can take any function from L1 and we can perform the Fourier transform, right?
Yes.
So it looks like the L1 space is a bit bigger than the Schwarz space. So
yes.
This was also understandable from the definition of Schwarz space. So when we take any L1 function, perform Fourier transform and back transform to the original time domain or original domain. So this can be regarded like as some projection operation to Schwarz space.
So if you take
some function from L1.
Yeah. So okay, I see. Because you're saying you apply it twice and you get the identity. So you apply it like it's almost right.
I don't apply it twice, but that way would also work. I transform and from that transformed function, I perform a back transform Fourier inversion.
Yeah, yeah.
So this would result some Schwarz function, I guess.
No. If you start with a Schwarz function.
Yeah, only in that case, okay.
Only in that case. Yeah, if you start with an L1 function, there's no guarantee that the Fourier transform that you get is integrable.
Yeah. Then can I apply your trick then, perform, but it will, then we could not be sure that we can apply
exactly. Yeah, you might not be able to apply another Fourier transform to it, right? Because so if you just take L1 function and do a Fourier transform of it, you might get something that's no longer integrable, and for which the Fourier transform doesn't necessarily make sense.
Yeah.
So that's the issue. So it's really most times with Fourier transform, it's convenient just to think of Fourier transform as Schwarz functions, because like if you just have a general one function, you take Fourier transform, you kind of have no idea what type of function you get, even if you get an integrable function or not. So Schwarz class, oftentimes many arguments go where you do some things in the Schwarz class and then try and approximate afterwards.
Yeah.
Because there's no guarantee that once you take Fourier transform, you get anything of just an L1 function, that you get something that's integrable.
Yeah. Okay.
But yeah, good.
Yeah. Thank you very much.
Thanks. Any other questions? And we can also keep chatting in office hours, of course.
Thank you.
Thanks, guys.
Thank you.
Bye-bye.